In this video, I'm going to show you a small shortcut for doing a trig substitution in an integral. Now, just to remind ourselves of when to use a trig substitution, I'm looking for integrals that have one of these roots in them, where I have an x squared and some constant. I'm adding and subtracting from one or the other. And depending on which one of these square roots I have, I'm going to have a different substitution. So if I have, for instance, in this first case, the square root of a number, a constant, minus x squared, then the substitution I'm going to use is x equals a, which is whatever's the square root of whatever's being squared in here, times the sine of theta. And I also have here the corresponding triangle that I would get for this particular substitution. And the whole idea behind this is I need that root to cancel out when I do the substitution, and so this is the substitution that will make that happen. Okay, there's the other two. When they're adding, instead of subtracting like the last one, I'm going to use a tangent, and when it's x squared minus a constant, I'll use secant. And those are the three different ways I would use this. So let's look at an example and let me show you the little shortcut. It saves you just a little bit of time and headache with the algebra when solving these using a trig substitution. So I have this integral here, the integral of dx over x to the fourth times the square root of 9 minus x squared. And so this is going to be the case where I use the sign, that first option that we had up there. And a is going to be 3 because 3 squared gives me 9. So the substitution I'm going to do is going to be x equals 3 sine of theta. Now, the whole idea behind this is kind of like a u substitution. I'm going to be swapping everything that has an x out for something in terms of theta. So the dx has to be swapped out, the x to the fourth, and the root. All of it has to be switched out for something. And so I have what x equals, so I know if I just take that to the fourth, I'll have the x to the fourth. I need to know what dx is, so I'm going to take the derivative of this, just like I would with a u substitution. And so the derivative of 3 sine theta is going to be 3 cosine theta d theta. So now I know what to swap the numerator out for. The only thing I don't have at this point is the root. And this is where the shortcut comes in, is in how do I figure out what that root is going to simplify to after doing my substitution. And I'm going to use the triangle for this. So let's set the triangle up. Here's my right triangle. I'll label theta right there. Now, to figure this out, because who wants to memorize those triangles up there, I use my original substitution here, that x equals 3 sine theta. If I divide the 3 over, I get what sine of theta is equal to in terms of x, so that would be x over 3. And so if I remember the triangle definition of sine, that is opposite over hypotenuse. So I know from this that the side opposite my angle theta is going to be x. So if I come over to my triangle, that will be x. And the hypotenuse is going to be 3. And if I use the Pythagorean theorem, then I will get the third side. But it should end up being my root here, the square root of 9 minus x squared. Okay? It should always end up being that root. If you're ever unsure about your setup, maybe you're doubtful on whether you got the right substitution at the start, you'll want to check that third side using the Pythagorean theorem, so x squared plus b squared equals c squared, to verify that you do have the root that you're dealing with in your integral. Okay, so now that I have my integral set up, the trick is to take the root over the constant in the triangle. It's what it's always going to be. Root over the constant, whatever those are. And I'm going to use triangle definitions again. So the root over the constant here is the adjacent side, I'll abbreviate ADJ, over the hypotenuse. That is what I grabbed when I did the root over the constant. And well, the adjacent over the hypotenuse, that's the triangle definition of cosine. So this is equal to cosine theta. And so to figure out what the root is equal to in terms of theta, I just multiply the 3 over. And so I get the square root of 9 minus x squared is equal to 3 cosine theta. And I didn't have to go through plugging in 3 sine theta into the root and simplifying that out. It saved me quite a bit of time just by using this little trick. And now I have everything that I need to do the substitution. I know what x is equal to, I know what dx is equal to, and I know what the root is equal to. And so I'm going to come back over to my integral and start working this problem out. It's a lot of setup at the beginning, but it really makes things go smoothly. So dx is equal to 3 cosine theta d theta. And x is equal to 3 sine theta. And so I'm going to take that to the 4th power. And then the root was equal to 3 cosine theta. So now I have swapped everything out for something in terms of theta, and I'm going to start simplifying. These 3's can cancel, and the cosines can cancel. And so I have just d theta left on the top. And on the bottom, 3 to the 4th is 81. I'm going to go ahead and pull that outside of the integral. So 1 over 81 ends up outside. And then I have sine of theta to the 4th power in there. Okay, so I have to figure out how to integrate this now that I've done the integral. And I don't like having a sign in the denominator if I can avoid it. So I'm going to use the reciprocal identity. 1 over sine of theta is equal to cosecant theta. So I'm going to go ahead and swap this out so that I don't have a fraction anymore. Just makes my life a little bit easier. So now I have 1 over 81 times the integral of cosecant to the 4th theta. And when I have powers of trig functions, I want to start thinking about identities that I can use to reduce that. And so the identity I want to use, let me write it off to the side here, is a Pythagorean identity. Cosecant squared theta is equal to cotangent squared theta plus 1. So I'm going to swap out one pair, two of the cosecants are going to come out of this. So I'm going to keep a cosecant squared and replace the other cosecant squared with cotangent squared theta plus 1 times cosecant squared theta d theta. Okay, so it may not look like we did much to help ourselves, but we're actually going to be able to do a u substitution now. Just like we did in the previous section where we were dealing with powers of trig functions in integral. And so just like we did back then, I want to choose the thing inside the parentheses, the trig function in there, to be my u. So u is going to be cotangent theta. And the derivative of u is negative cosecant squared theta d theta. Okay, so if I come back over here, move a little bit over, run out of room. The negative I'll put out front from the du, swapping that out. And then cosecant d theta, that's going to be replaced with du. So I'm just going to have the integral of u squared plus 1 du. That just swaps everything out, and I have a nice polynomial inside of my integral to integrate now. So I've got negative 1 over 81 times, and then the integral, that's going to be 1/3 u cubed plus u, and plus c for the constant of integration on the outside. Okay, so the hardest work is over. I've integrated it. I just need to get myself all the way back to the x's that I started with at the beginning of this problem. So first I'll swap out the u's for thetas. So negative 1 over 81 times, and actually let's go ahead and distribute that at the same time, start simplifying things. So 1 over 81 times 1/3, that's going to be negative 1 over 243. And then u was cotangent, so I get cotangent cubed theta, minus 181, just distributing the constant from out front, times cotangent of theta plus c. Okay, so I reversed my second substitution. I'm back in thetas. Now I need to get back to x. And so I go back to my triangle. So cotangent, if we come off to the side here, cotangent of theta, that is adjacent over opposite in my triangle. And so the adjacent side would be the root, 9 minus x squared, square root. And the opposite is x. So that is what cotangent is equal to, and that's what I will swap it out for in the problem. So negative 1 over 243. And let's turn this into one fraction as I look at it. So on the top, I've got 9 minus x squared. It's being square rooted and taken to the third power. So that would be the 3/2 power. That's how I'm going to write that. And then I've got the 243 on the bottom and an x on the bottom. And then minus. And, I don't know where that t came from in there. That should have been cotangent, not cosine t. There we go. And then cotangent theta, that's going to be just the root again. So I'll leave it as a root and throw the 81 and the x on the bottom, plus the constant integration. And now I have my final answer. So the key takeaway here is when it's time to swap out the root for something in terms of theta, use that triangle and always take the root wherever it is, divided by the constant wherever it is, and then figure out which trig function that defines and set it equal to that. And that is how you use this shortcut for a trig substitution.